we call the size of a set A countable infinite if the cardinality, that means number of elements in A, and it's the same as the number of elements in natural number. So the idea is you create bijective function. So injective, this guy do not share the same y. This is impossible. So you have this, but I didn't draw the shape here, right? Surjective means everybody here is mapped up by something. So these two together, you have a 1-1 correspondence. Let's say I know A, and I know the number of elements in A, and suppose now I want to count the number of elements B here. But because I have 1-1 correspondence, I just need to count the number of arrow here. Then, because the number of arrow is from each individual here, and none of them share the same element here, that means injective, and all elements here have been mapped surjective, that means because of this property, what's the size of B? It's just size of A. So the set of even integer has the same cardinality of all the natural number. You may think that this is crazy. Okay, let me explain why you have this feeling. You probably have this feeling because of the following picture. This is my set A. I dig a hole and I remove everything. This is not counted in A, and the remaining part is my B. Then B is a subset of A, right? Then you probably will think that, okay, in this case, size of A is larger than the size of B. I mean cardinality. Let me say this. This is true only if you have finite number of things. This is not true if you have infinite number of things. So suppose my A 1 to let's say 100, all the integer. And let's say my even set is, okay, all the A set subtraction or set complement, all the odd number. So I'm removing all the odd number. That means 1, 3, 5, 7, blah, blah, blah. So of course, this is true because this is finite. When things go to infinity, crazy things happen. This is not true in infinity. That means if I have this, I go to infinity. Then these two sets have the same number of elements because of the figure I just showed. This figure says that if I have a bijective map from A to B, then they have the same cardinality. This is exactly what a bijective map. Now label 2 as 1, label 4 as the second number, label 6 as my third number, label 8 as my fourth number, and I can always do this, right? So this is a bijective map. So whatever you give me a number in E, I can give you a number in N. And whenever you give me a number in N, I can give you a number in E. There will be no two number in N share the same number in E. And there are no two number in E share the same number in N. So I can go back and forth, and all the matching is 1 to 1. Basically, the point is this argument only works in finite sets. Now we are considering infinite sets. And this is by definition, that's why I have a symbol. This means define. Why we can say this equal sign. If you can give me this bijective map, then you can say this is true. Because for this kind of thing to hold, nobody said this A has to be finite. I can make the picture that looks like this. It can go down, and this arrow is still true. But the point is, this figure can become infinitely long. I just didn't draw the remaining part. But this argument is still true. And also, recall what's the definition of bijective. Bijective is injective and surjective. What's the definition of injective, surjective? It's just no two X share the same Y, and all Y have to matter. The two definitions here have never mentioned the set A and set B is finite. It can have 2 elements, 2,000 elements, or infinitely many elements. So this is the first example. Then, similarly, the second example, you have the same idea. This is a bijective map. You are labeling this number by n. You can think of n is like the order of this number. Technical name, these are called ordinal. That means order number. The size of a set is called cardinal. That means cardinality. Now the set of all the square of natural number has the same cardinality of natural number. 1, 1, 2 to 4, 3 to 9, 4 to 16. Well, 1, 1 correspondent. So these two sets have the same cardinality. And I make a mistake, this is S, so this should be S, not E. Okay, again, I make a mistake, this should be S. I have a set that power n15. So immediately the second number is already bigger than the computer can show. This set is also have the same size, that means cardinality, as n. Again, you will feel that, no, I take something out. This set B is smaller than A, so this should be true. But now I'm showing they are equal. This thinking, this perception is true for finite sets. This is not true for infinite set. The intuition is like this. If I have an infinite set, think of it as a very long line, and then you take something out, so something in A is not in B. But since your set is infinitely big, when you zoom out, you don't see that thing. And this actually is also the beginning idea of calculus. That is, something extremely small, you don't see it when you go to infinity. N to the n power factorial is also have the same size as the n. Okay, again, this is S. And the same, n to the power n to the power n to the power n factorial has the same cardinality of n. Because you can always construct this, then they have the same cardinality. All this set, that means from this arrow to this, all have same number of elements. These are just one-dimensional set, so you have a list of number. What about two-dimensional set? 2D grid has the same number of points. as a line grid. What is n? It is like what? You have a point here called 1, a point here called 2, a point here called 3, a point here called 4. So it's like a grid, right? Now I'm telling you, if my grid is two-dimensional, it has the same number of points as my one-dimensional grid. So 2D is 1D. If you have a way to write down one correspondent from a set A to set B, immediately the two sets have the same size. This is the way. You start with 1, because you have two-dimensional points, so now you have what? A Cartesian product n cross n. Then you start with 1. Then what? The difficult part here is you need to find the bijection. So you draw a line that looks like this. This line will go through all the points, right? And this is a line, right? Do not care about the shape. Think about this as an elastic string, as a straight line. Once you have two straight lines that look like this, okay? Then this line and this line, 1 correspond. That means what? I now label my number in this funny way, not as simple as this. This is easy, right? For even number, I just 2, 4, 6, 8, and so on. So 1, 2, 3, 4 map to 2, 4, 6, 8. But this one, not that easy. My first number is 1, and then 2, 1, 1, 2, 1, 3, 2, 2, 3, 1. What are these? The first, and then these two, what? The coordinate sum to what? 3. And then what are these? The coordinate all sum to 4. So you are actually have a line somehow grow in this direction. So basically you are drawing a line that looks like this. And if this is a line, then this is also a line, then you have 2 lines, and 2 lines have the same number of points. And then with this idea, then 3D cube and 1D line have the same size. 4D cube and 1D line have the same size. N cross n cross n, that means a 3D cube have the same number of points as a line. N cross n cross n cross n cross n, how many times? M times. Also have the same cardinality of n. You may wonder, what happens if this becomes cardinality of n? That means I have infinite number of Cartesian product here. What happens? Later.